Yeah, that's right. Yeah, thanks, Manu. Okay, good morning, everybody. A few of us are going to be talking about the Insight project. I'll begin. I'm an innovation project manager at SSCN Transmission. If you go to the next slide, please. So the problem we are facing as an industry is a result of unprecedented uptake of new cleaner energy sources on the journey to net zero, which is causing new types of oscillation on the electricity networks, not just in the UK, but across the world. So why is there a problem? Well, there's a move from fossil-based power generation using heavy synchronous machinery, such as gas turbines, which are effectively constant in their power delivery due to the large inertia of the system. However, asynchronous renewable resources, such as wind and solar, are very intermittent just by their very nature and pose a new challenge to our networks. Within the UK electricity network, we operate at a frequency of 50 hertz, and this must be maintained continuously 24/7 within a very narrow range, and that range is typically 0.2 hertz at the side of the 50 in order to maintain a safe operation. And traditionally, electricity generators are high inertia systems, as I mentioned. They can cope with high transient instabilities, but new technologies are required for new renewable energy sources, and they are low typically in inertia. And these technologies are based on power electronics and often referred to as inertia-based resources. So just before we move over to Jacob, I'll just mention the partners. So that we've got University of Strathclyde, who are looking at state of the art in understanding oscillation methodology and modeling, which is a very complex subject. The National HVDC Centre, who've gone out to the industry for a stakeholder engagement, both in the UK and further afield. National Grid, ESO, and ourselves, we're providing information on oscillation events and historical experience. So over to Jacob for the next slide.
Hello, yes, I'm Jacob Kelly. I'm a Transmission Operation and Planning Engineer at SSCN Transmission. So I'm just going to have a quick overview of the project, what its objectives are, the benefits, and what we did in discovery phase. So the real sort of long-term objective of the project is to try and deliver a virtual real-time alert and control system that can monitor and then provide actions to mitigate different types of oscillation events experienced on the network. If we can do this, we can improve the network stability and reliability. We can reduce the likelihood of network disruptions, and it is potentially a low-cost solution that does not require the contracting of expensive stability resources, either bringing on existing power stations or constructing new synchronous plant to provide that stability to the system. It also allows us to sort of act and react in real time to events that we haven't been predicted in the planning phases. So that's where it helps improve the kind of resilience of the network as well. So throughout the discovery phase of this project, we've been looking kind of globally and within the UK to get a real understanding of the problem and the best practice of what other people have done, where the industry's at, kind of what the kind of tools are that are available just now and where they look like they're going in the future. And we've investigated the kind of models and tools that we can use to simulate these network events, the kind of patterns they are, and look at how we can use those to design a system that can do this. Because one of the key things in designing this is we need to be able to test it in a meaningful way. Next slide.
Hi, my name's Fabian Moore. I'm from the HVDC Centre, and we sort of led a bit of work on stakeholder engagement and trying to find out what the rest of the industry is doing. So we sent out an industry survey to 55 different organisations from across the electricity industry. We got 32 responses, including 11 from different system operators and owners. So that's across the UK, but also including Europe and other countries across the world. And so just as a pie chart there, just showing who responded to the surveys. And the largest category is other, and I think those are generally industry-led research groups or academic universities as well, and consultants. But the largest sort of industry group that I guess we're familiar with is the network owner and operator. So that's our background. And next slide, please. So just to summarize what we learned in the survey, it's quite hard. We had a number of questions on a variety of topics, well, related to the topic about modeling and measurement of this phenomena, these kind of oscillations, power electronics. And I think the takeaway was, although most system operators and owners had some capability to detect and analyze these oscillations, they were all concerned about their capability not being sufficient in future. There's an increased risk of inverter-based oscillations in future because there are getting more and more of these renewable energy devices. At the same time, existing monitoring systems are very reliant on sort of manual analysis. Although if you look at the graph on the right-hand side there, sort of how people use their monitoring systems, the majority of utilities were using them in post-event analysis. So having had an event, an experienced event, then digging through the measurement data after the event to understand what happened. And there's very limited use of real-time monitoring to human operators or feeding into real-time automated systems. So I guess the takeaway was that although we can analyze these events, I think they kind of get swamped if we get more and more events, and we need something cleverer to manage and look at the data. So it kind of supports the aims of the project, really. And yeah, that's me. So next slide, and I think we're back to Jacob for a slide.
Yes, so I'm going to cover quickly, I think, one of the reasons that we've got some opportunities to really address this problem, both through the project and through the wider industry kind of position that we're in at the minute. There's been a lot of kind of work on innovation projects and elsewhere on looking at collecting the kind of data you need to monitor these oscillations. You need high sample rate, high resolution data collected centrally to be able to analyze these events. So the VISOR project, the previous SIF innovation project, looked at these events and sort of collected that data into a collection system. And as part of the outcomes of that, there's PMU deployments across the UK, both in our network. Scottish Power already have a lot deployed, and National Grid are looking at the same. National Grid then get this as part of the SCCP 27.1, so a new transmission owners code of practice. We need to install these PMUs for visibility. So there is going to be lots of data available from the network to look to address these issues. It's also the case that yes, the IBRs are kind of coming into the network. They don't have the same system stability benefits of a standard synchronous machine, but they have a lot of really useful technical capabilities that can be used to mitigate these events themselves. And they've got very large megavar ranges. They can be designed to have power oscillation damping as part of their control systems, and you can change their control modes on the fly effectively. You know, if you design it such that way you can change those control modes. They are just effectively computer system control modes, so they can be changed. You can't change the properties of your synchronous machine, but you can on your power electronic device. Next slide, please.
Right, hello everyone, Jitan Hong here from Strathclyde University. I'm the academic lead from the project from Strathclyde. So in the project, in addition to the survey Fabio mentioned earlier of the stakeholders, we also conduct a survey of real-world oscillation events. So basically, we look at what happened around the world, and what we found is that Scotland is certainly not alone seeing this phenomenon, and we see many other countries like Australia, US, China, they have similar events happening increasingly in the past several years, mainly particularly in the area with high penetration of renewables. And then we look into the details about the fundamental mechanism of this new oscillation and evaluate the existing and also emerging measurement, monitoring, and control solutions. And what we found that is the IBR-driven oscillation, and a unique feature is that a majority of them are caused by the controller design of the IBR units or the control interruption. And the frequency range of the new oscillation can be much wider compared with what we've seen conventionally in the system. And that leads to the existing monitoring device like PMU may not be adequate, and we might need something with higher resolution. And we look at the existing solution as well. Vast majority of them still focusing on relatively lower frequency oscillation. And there are emerging solutions being proposed. However, they're either in R&D stage or they're limited real-time mitigation capability available. So something further are required to address the challenge we are facing right now. And next slide, please. So in order to better understand the phenomenon, and in addition to literature review, we also investigate how we can model, simulate, and replicate those events in our lab or in our platforms in alpha phase. So we look at the high fidelity EMT modeling. We also look at relatively lower fidelity based domain. And we also look at how other people around the world has simulate or replicate those events to gain the experience. And then we develop the modeling and simulation requirements for us to pursue in the alpha phase. So what we found is EMT modeling is what we want to proceed because of the wider range of frequency of the oscillation we are targeting. And we also found that ideally we should aim for vendor-specific detailed controller model from manufacturers, even though it could be black box. Although it is possible to use generic model, but it is ideal to use vendor-specific model, given the dependency of the oscillation on the controller design. On the right-hand side, you can see a modeling kind of a plan we come up with from first stage targeting the oscillation type and area we want to target, to collecting the required data we need, and then on the third stage is developing the real-time model in RTDS simulator, and that is the key stage we are going to pursue in alpha phase. Help us to understand the oscillation better, but also it allows us to further develop it to enable real-time testing of potential insight solutions and beyond beta through hardware in the loop, closed loop testing. And we are going to pursue beyond alpha phase. So that's me. I'll hand it over to, I think it's David or Jakob.
I think it's me again this time. I'm going to quickly run over some of the sort of potential benefits of the project. So I think the key thing with this project is that the benefits of it are kind of the end goal has benefits, but every step along the way, every sort of step we do in terms of further understanding these events in and of itself introduces a lot of benefits to understanding the system, understanding how we can plan it and operate it going forward into the future. If we can deliver a system that does real-time kind of monitoring, alarming and control, it really does improve that system visibility. By doing that, you improve your resilience and reliability of the system. If we can do that, we can provide actions for real-time sort of mitigation of oscillation events. We can respond to sort of real-time system issues, improving the reliability and resilience of the system. And it also then lets us, even if an event hasn't been predicted through the models we've created or in the system planning stages, it allows us to still respond to it. So it gives you that kind of resilience and reliability to unforeseen future events. And what it also does is it uses the sort of inherent capabilities and benefits of IBRs in terms of inverter-based resources, in terms of they can have control modes. Yes, the control interactions is the driver of a lot of these, but you can change them. They can be changed. Their computer software. They can be altered. They can be used, and it's trying to sort of make benefit and use those tools that are coming to help increase the system reliability. Next slide again.
Yeah, back a slide, please. So good afternoon, I'm David Gregory from ESO. I'm a power system engineer and network operability team. So just want to give a few thoughts on how our thinking of the project has evolved. So initially we were looking at allowing real-time control of TO devices to damp oscillations, but there is a broader picture here, so we start thinking about how you apply it to the GB networks. We talked about use of IBRs, inverter-based resources. So is there scope there to assess users' assets' ability to dampen these oscillations? So you can then sort of start tailoring the response to an event on the system. Can we determine who's the most effective to damping an oscillatory mode, which would be kind of give us a lot more flexibility in terms of system operation. Does raise questions there about, is that the right approach? These sort of types of instabilities are intended to be designed out, so the grid code currently places the onus on users to assess and address those kind of behaviors and mitigate them before connecting. So I mean, it does raise sort of wider questions about, is that the right way forward? But that's kind of where our thinking is on how this project could be taken forward. So move on to the next slide, and thanks back to Jacob.
Yes, so we've talked about kind of what the gaps gaps are in terms of the current approaches, what we need to do going forward. I think I'd like to sort of cover on to what we think we can do in the next alpha phase and where we think we can go forward in terms of the Insight project. So the Insight project, we're really going to look at what can be done with higher resolution data, using PMUs, using waveform data that's out there, using WMUs, which are even higher resolution versions of PMUs, and look at what real-time control actions can actually be applied using the expertise of the HVDC Centre, and looking to come up with a kind of validation methodology for techniques for both monitoring and alarming for these events, but also then applying those mitigation actions. So I think the key thing we're looking at is how do we create a sort of testbed platform for different solutions that can be used to assess what is the best action to take in the event of one of these things occurring, and how do we prove that that's the right action to take, and how do we test what the approach is to do that. Thank you very much. I think that's all we have from ourselves today, and if you've got any questions, please let us know.
Brilliant. Thank you so much. Thanks, Jacob. Thanks, David, Chitang, and Jonathan for the presentation. Yeah, again, quite a fascinating kind of project, looking at what some of the issues could be in kind of future stability on the power system. So I think I'm not seeing any questions, but I think we've got a couple of minutes. I've got a couple of questions, if that's okay, just to kick us off, maybe until that time will come. I guess the first one is, you looked at kind of international experience, and I think you did some surveys, etc. Like, what are the key learnings from other countries? Is UK going to be facing some of these issues earlier than some of the other countries? Because I know US, some states particularly, have looked at kind of inverter-based resources and impact on power systems. Like, is there any learnings on what they've found and which direction they've kind of gone in terms of potentially either market-based approach or the kind of mandatory requirements on some of these assets to kind of dampen, etc.? Like, any learnings from international experience?
Should I answer this one as I did the survey? So I think internationally, all utilities are experiencing similar type oscillations and problems that they've got to manage as a result of the move to power electronic devices and away from traditional generation. And I think that most people are relying on the traditional approach that sort of David outlined, of talking about trying to get people to do compliance by doing studies up front. But I think that the sort of gap in that is that people still connect things. They think they've solved everything, and then something comes out of the woodwork after something's been designed, and try to understand it and adapt the control or design of equipment so that it gets fixed. And I think all utilities are using this post-event analysis, where they dig out the measured data from all the devices they can see the oscillation on and try to understand what happened. And it's quite a laborious process. But I think, the state of the art in terms of, Strathclyde looked at the simulation and calculations, but everyone's trying to find ways to solve these problems. And we've got kind of a suite of tools for solving these problems, but trying to do it in a slick, quick way. I think there isn't an easy way. So trying to think of a more clever way forward is kind of where this project goes.
Can I quickly just add a comment, please, Mano? So basically, I think what we found is obviously many countries are seeing those events increasingly, and what they have done right now is kind of they see the events, and then as Fabian mentioned, they take out the results, and then they do the analysis and try to analyze what happened, and then try to come out with something. But obviously there's no kind of systematic solution saying, okay, if something happened in real time, I know what I should do. And the danger there for now is the potential cause of this type of oscillation can be very diverse, and it can get more and more frequently happen, particularly when the system has low demand and a lot of renewable connected. So I think we are looking for is something more comprehensively understood, tested, and something is more readily or quicker to respond with informed decision making, with confidence as well. I think that is something. I think through the survey with the stakeholders, I think there's general feedback we got. They do have something. Most of them, they say they have something available, but most of them don't feel confident it is adequate. And I believe that is something, and the value that this project can bring to build the gap, basically.
I think maybe time for one more question. I think there's one in the chat. What are the kind of most common root causes of these events?
I think I can take this one. So I can see in the chat I share, so depends on different type of oscillation, but what we are focusing on is a new type of oscillation induced by the renewable generation, inverter interface renewable generator. And vast majority of them are caused by the controller design. So different manufacturers, they implement the controller in different ways and tune their controllers in different ways without a good knowledge about what other controllers are doing. So for example, you might have a wind farm in one location, and then somewhere you have a HVDC converter nearby. And the manufacturers of these controllers, they don't know what the other controllers are doing. So unintentionally or some kind of occasionally that might interrupt undesirably, and that is, I think, more than 50% of the event is caused by the controller interruption, and that is the main root cause. And the issue there is that the controller design can be so diverse. So this undesirable interruption could be something we know already, but it's something else, another type of frequency, another range of frequency might observe in the future. So that is something making the issue more challenging.